Hello there, another lesson on sequences, this time geometric sequences, which we've kind of seen before, but perhaps never given them a name. A geometric sequence is, well, here's an example, it's 2 I'm going to start with. I'm going to times that by 5, 10. I'm going to times it by 5 again, 50. And times it by 5 again, 250. You can see every time I'm multiplying by the same number. So unlike arithmetic sequences where you add on the same number, here we're times them by the same number each time. I mean, you can divide as well. So if I pick a bigger number like 1024, and each time I'm going to divide by 4. So I reckon that's 256. Divide by 4 again. I reckon 64. So doing the same thing each time. Divide by 4 again. I get 16. You can see I can keep doing that. And eventually, if I do it, I'll eventually get decimals, which is fine. You're allowed to do that. You can keep going. These are geometric sequences. Either times or divide by the same amount each time. Now, here's a little starter for us. Zarathustra, living in Persia. Now, Persia is part of Iran these days. But a long time ago, apparently the legend goes that he invented a game of chess. And it was to please his king. And his king was so happy, he said to him, look, you can have anything you want. You ask for your reward, and it should be yours. So Zarathustra thought, I'll be a bit crafty here. I'll ask for this, and he wants grain. Grain, of course, was something which you can make flour out of. Flour, you can make bread. You could see it was a valuable commodity, and still is. So he asked for 1 grain of whatever, barley or wheat, whatever it was, to be placed on the chessboard in the first square. And he said, I'll just simply give me 2 on the next one, and 4 on the next one, and keep going until you eventually filled the board. And so he kept going. And I suppose Zarathustra thought, I'm being sneaky here. It looks like a very small amount. It does, doesn't it? So you've got 1, 2, 4, then 8 on the first 4 on this board, doubling each time. And the question is, how much would have to be placed on the last square, this one over here, presumably, this square here. And well, I suppose this is, on the first one, this is 2 to the 0. 2 to the 0 equals 1. This is 2 squared, which is, 2 to the 1, sorry, which is 2. This is the 2 squared, which is 4. And this is the 2 cubed, which is 8. So the fourth one is 2 cubed. I reckon this one would therefore be 2 to the 63, because you've got to knock off 1. You always knock off 1. And, of course, if you type in 2 to the 63, I'm just going to do it on my calculator now. See if the calculator can cope with that. 2 to the power of 63. I wouldn't be surprised if it said go away. No, it does squeeze it on, but it's 9.22 times 10 to the 18. So there's 18 noughts. Well, 16 more noughts after this 9.22. That's a big old number. That would have been a lot of bags of grain. And apparently the legend goes the king wasn't too happy when he sussed how much grain he was given to this man. I don't know, who knows, chopped off his head. I don't know the full story. I wasn't there. There you go, a lot of grain. So geometric sequences then can get big quite quickly. I suppose that's what that story told us. And 2, 6, 18, 54, 162, you can see they're getting big each time quite quickly. That's just a simple times by 3. But then you keep on doing times by 3, and eventually you get 162, and then 486. You know what I mean? It gets big quickly because we're multiplying, not adding, we're multiplying. And these sequences are called geometric sequences. And a bit like when we did arithmetic sequences, we had a common difference. Now we have a common ratio. And to find the common ratio, you divide one term by the other. So 6 divided by 2. Notice 6 divided by the one before it. It is 3. Or you could have picked another one, any one, 54 for instance, divided by the 18. It's also 3. Just pick any one you like and divide by the one before it. So there's I did 6's into 18 to get the same answer. And notice we write this with a lowercase r equals 3. Common ratio, r equals 3. So the first term, you get a. I'm saying we'll call it a. Second term, we'll say it's a times by whatever the common ratio is, ar. And then we'll times by r again. And then we're times by r again. So you'll notice each time I'm getting a, ar, ar squared, ar cubed. This, of course, is the first term. this is the second term, this is the third term, and you quickly realize the term number, you have to take away 1 to get the power. And so for that reason, that's A and that's R, the common ratio. For that reason, you'll notice the nth term of a geometric progression, as it's sometimes called, or a geometric sequence, is un equals AR to the n minus 1. It's not in the formula book. You're going to have to learn it. Write it down, please. And to divide, this is a reminder really, to find the common ratio, divide any term by its previous term. Okay, so our first question, use the formula for the geometric sequences to find the terms integrated. Okay, then fair enough. So we've got 2, 8 and 32. So what have I got? I've got A equals 2, the first term. Now if I just divide one by the other, I get 4. So I get R equals to 4. So I want the sixth term. So U6 equals A2 times R to the n minus 1. And that's to the 5. So, okay, might as well type that into a calculator. So 2 times 4 to the power of 5. 2048. Okay, so just going to do a few of these. Each time I'm going to write down what the value of A is. A is 12 in this case. They tell me they're geometric, so I don't have to worry about any, are they or aren't they? And then the R, again, what you've got to do is you've got to do minus 3 divided by 12. I reckon it's minus a quarter. And you could pick any, but minus 3 divided by 12, do it that way round. So what is, I want the fifth term, so it's 12 times by minus a quarter to the power of, you want always to knock one off, so it's to the power of 4. So 12 times by, and it's definitely worth doing this on your calculator, I think, because you'll probably go wrong otherwise. And I get 3 over 64. Make sure that minus is in a bracket with the quarter. And the third one, C, I just want the nth term this time, so we're going to leave it as like a formula approach. So A equals 0.2. Again, we've got to divide that by that, and if you divide 0.02 by 0.2, you get 0.1. So, or a tenth. I'm sticking with decimals. R equals 0.1. So my UN term here, what is it? It's A 0.2 times by 0.1 to the n minus 1. And they don't tell me which term they want, so I've got to leave it as an n, as a power. Yeah, they've done exactly the same as me. And then D, what's this? 268. Which term is equal to? All right, now this is different. So I've got to get the formula. So I'll do that first of all. A equals, you can see it's 6 divided by 2 is 3. R equals, did it the wrong way around. A is 2, R is 3. And therefore my formula UN equals A times 3 to the n minus 1. And it says which term is equal to 3, 5, 4, 2, 9, 4. Now I've got to solve an equation for this. So first job is move the 2 over. 3 to the n minus 1 equals. And what is that? 3, 5, 4, 2, 9, 4 divided by, I'm moving the 2 over, divided by 2. And I get 1, 7. 7, 1, 4, 7. Now to do this, of course we've got this posh button, haven't we? We've got on the calculator, we've got well, I suppose the trick is to suss that when we move this 3 over, the n minus 1 will become log to the base 3. That's what we've seen when we've done logarithms of that. So if I do that, now that has got its own button, so log to the base 3 of 177147. I get 11. So n minus 1 is 11, and I reckon therefore n is 12. 12th term, that's right. I haven't seen E yet, so let's do E. In this term, they are consecutive terms of a geometric sequence. Well, we saw a similar one to this with arithmetic. And what we're going to do is we've got to say that this divided by this has got to be the same as this divided by this. I'm going to try and squeeze this into this tiny little gap I've got here. X plus 1 over x minus 3 has got to equal that one, 3x minus 5, divided by the x plus 1, because both of them have to equal the same common ratio. That's basically the logic. And I've got the answers here, 1 and 7, but let's see if we can get that. Now, cross multiply. Get that up there, get that up there. So I've got x plus 1 times by x plus 1. And that's got to equal 3x minus 5 times by x minus 3. So multiply that out, I get x squared plus 2x plus 1. And that's equal to 3x squared. That's minus 9, I reckon minus 14x plus 15. And I'm probably going to move everything over to here. And that gives me 2x squared on the right hand side, minus 16x plus 14 equals 0. That gives me x squared, if I divide everything by 2, plus 7. And I reckon therefore x minus 1, x minus 7, so x equals, according to me, 1 or 7, which is good because that's what the answer is down here. And then the final question on this slide is the fourth term of a geometric sequence is minus 6. Again, I've got to do a bit of work here. Let's see if I can squeeze this in. So the fourth term, now when we did this with APs, I made you write out the formula, so I'm just going to do it here. U4 does say the fourth term, does it? Yes. Which is AR to the 3, always take off 1, equals minus 6. And U7 equals, well, AR to the 6, and that equals 48. Now, when you do these, you have to do a division. So I'm going to divide going up. And the great thing about doing that is AR to the 6 divided by AR cubed on this side equals 48 divided by the minus 6. And the reason why I say the great thing is the A's cancel, lots of the R's cancel, and you take away the powers. That's, remember, the trick from what we've seen in the past. So R cubed equals, what's that? That's minus 8. So therefore R must equal minus 2, and I cube root it. So once I've got that, I just realised what the question said. So find the first 3 terms. So now I've got R equals minus 2. I suppose I've got to go back and find what the A is as well. So what's the A? Well, minus 2 cubed is minus 8. We've just said that. So therefore A times by minus 8 equals minus 6, subbing into this equation here. So therefore A equals minus 6 over minus 8, which is 3/4. So at long last I've got that. That's where that 3/4 comes from. But to get the other ones, I times by minus 2, and 3/4 times by minus 2 is minus, well, 3 over 2, or minus 1/2. Double it again to minus 3. Yeah, I can see they are right. This is the last question. The first term of a geometric sequence is 10. Well, straight away, A equals 10, and the common ratio is a third. All right, that's nice. Which is the first term less than 10 to the minus 6? Well, 10 to the minus 6 is 0.00000, 6 noughts, and then a 1. So I've got to have this. So A, this is my formula, R to the n minus 1. This was my nth term. So in this case, we've got 10 times by a third to the power of n minus 1, which I don't know. And that is equal to, I'm going to set it equal to, I suppose technically it's less than I want, but it's easy if you set it equal to. And that is equal to this 0.0000001. Move the 10 over, well, that makes it even smaller. And then n minus 1 then is that log to the base of a third of this horrible number. So I'm going to do that now. And I get n minus 1 when I do this equal to 14.67. So therefore n is 15.67. That's the first term. Well, I can't have that. So the first term I think is 16. And let's see what the answers say. 16th term, good. Notice the decimal answer, you have to go a bit higher than it so that you go lower than this value. Look, exercise 4e, page 79. We'll do this in class, and it's a nice topic.